soon after, in 1909, we find the word gene.
It's a real honor to, first of all, to congratulate the university on its amazing accomplishments in precision medicine, which are in the past, but also about to begin now with this astonishing series of collaborations that have been launched. So congratulations to all of you. I was at dinner last night hearing about all the new initiatives that will begin across the university, across the collaborative campuses, and really make Chicago and this university one of the hubs, proud hubs of precision medicine in the country. Obviously, I'm an oncologist, and I wanted to give you a sense of what precision medicine looks like from the perspective of cancer. So I'll focus on cancer in particular. My area is leukemias and lymphomas, although I certainly see breast cancers and other cancers. But remember that this kind of idea, I think, is probably quite general for medicine. In fact, cancer is the model by which precision medicine will be brought about in the world, partly, of course, because cancer is such a powerfully genetic illness. The influence of genes is so powerful. So let me begin by identifying kind of a moment to start the discussion with Rudolf Virchow. Virchow, as many of you know, was a famous pathologist, and as a young man, Virchow made the striking discovery that regardless of the tissue of origin, whether it was brain or whether it was lung, whether it was liver, etc., that cancers were characterized by a very common phenomenon. That common phenomenon was the fact that cells were dividing abnormally, they were growing abnormally where they should not have been growing, and that they had refused to respect the normal boundaries of cellular growth, the normal boundaries of cellular control. Now, that itself was, of course, a radical and important observation. There had been all sorts of theories of cancer before Virchow, but Virchow made a second observation. Virchow's second observation was that he made the argument that all cells came from other cells. So if that's true, if all cells had to come from other cells, then ipso facto, it has to be also true that a cancer cell must arise from a normal cell. And if that's true, if it's true that a cancer cell must arise from a normal cell, then something must have happened to a normal cell to convert it into a cancer cell. Just from simple observations, Virchow had essentially created a transformative theory of cancer, that some event occurred in a normal cell that allowed this normal cell to fail to obey the boundaries of normal growth, normal metabolism, normal occupation of tissue space, break those boundaries and begin to proliferate and grow abnormally. That process was eventually called transformation, but no one knew what transformation was. And the question that you could ask yourself sitting today was, is it true that in all of the transformations that occur in breast, in lung, in blood, etc., all these different kinds of cancer, is it the same process? Is it different processes? And if they're different processes, should the same medicine be applied to them or different medicines be applied to them? So in other words, astonishingly, the whole root of what we now think about as targeted therapies in cancer, and similarly precision medicine in cancer, is rooted in the idea of cancer itself. It comes from the very, very earliest way of thinking about cancer and the riddles and puzzles that were raised at that time. I'm going to try to move on to the next idea, which is, again, the question of what was transformation then? If that was the case, what was the cause of transformation? And there were four major clues, and you could imagine that there were four sort of battling clues, because there seemed to be four sides to the same problem. You think about the proverbial elephant and the blind man. In this case, it was cancer and blind scientists trying to figure out what was that transformation process? What had led this perfectly good citizen cell to become now a bad citizen cell? And obviously, one major source potential was heredity. That's a picture of Hilario de Juvia, the Brazilian ophthalmologist, who made the point that cancer, at least in his case, retinoblastoma, retinal cancer, seemed to run in families. So he had observed one family where it was a very clear hereditary pattern. So he knew that heredity had to do something with this. Even before the Brazilian ophthalmologist Percival Pott in England had very clearly observed that, aside from cancer running in families, so this was earlier, Percival Pott had observed that certain professions were highly likely to get certain cancers. And in Percival Pott's case, it was chimney sweeps were very highly likely to get scrotal cancer. Young men who swept chimneys were very likely, by a factor of, it stuck out epidemiologically like a sore thumb, the idea that young men with chimney sweeping as their profession used to have a huge high incidence of scrotal cancer. So clearly, the environment had a role. There was a role of chance. In some families, for instance, with breast cancer, not all women would get breast cancer. That was one observation. But also, some women would get breast cancer quite late. Some would get early. No one exactly knew what the role was. And then Peyton Rouse in New York had observed that, at least in animal models, he could use viruses to create cancer. So there was a question, which of these four causes was the real root cause of cancer, and how could that possibly be related to this phenomenon of transformation? And the solution to that came in a kind of blazing, important clues in the 1970s and 1980s, and it was a very simple idea. And that idea was genes. So in other words, alterations in growth-controlling genes cause cancer. Now we know it a little bit more broadly. We think that alterations in growth, metabolism, differentiation, anything that ultimately impinges on a decision of a cell to divide or to grow, alterations in those genes cause cancer. This was work done by many people. I've just outlined some people here, Harold Varmus and Michael Bishop, Bert Vogelstein, Janet Rowley, Bob Weinberg. Several laboratories contributed to this idea, but ultimately it converged, as I said, on a simple thought and that explained this conundrum. Because of course you can inherit the genes, you can get it from your parents, hence cancers running in families like BRCA1, for instance, retinoblastoma. You can get the genes the genes can be mutated by the environment. So the environment, carcinogens, in fact, Percival Pott coined the term carcinogen. You can have environmental agents that make the genes alter, mutate, and thereby cause cancer. Chance plays a role because when cells divide, they can make errors, and when you make an error, you can introduce a mutation and thereby cause cancer. And viruses can bring the same genetic information into the cell or disrupt the genetic information of a cell and thereby cause the same process. So all of a sudden, this seemingly mystery of multiple causes converged on a very simple idea, and that is that a distortion of normalcy, the very genes that control normal growth and development, if you disrupt them, if you distort them by mutations, then you will essentially unleash the malignant process, answering Virchow's riddle of transformation. That was all very good news. So the 1970s, 1980s was mostly a news that really consolidated the field and made it possible to think about this field in a more sort of homogeneous, systematic, and consolidated manner. Then there was a series of questions that begins our sort of more contemporary era of cancer. And I'm going to continue the thought here. So again, alterations in growth-controlling genes cause cancer, and the question was how many and how common. So for instance, is it one gene per cancer? If you look across multiple cancers, is it the same gene? What is the relationship then between genes and cancers if you understand that there are many, many different kinds of cancers in the world, and of course there are about 23,000 odd genes that we have as humans. So how would you put these two pieces together? And the first idea came from work done by several people. This is from Bert Vogelstein's group. And that was that one gene was not sufficient. So for most cancers, although there's exceptions to this, for most cancers, you had to have many genes had to be mutated, often sequentially, to ultimately cause cancer. Vogelstein occasionally has described these diagrams. It's a kind of malignant slouch. You start with one mutation in a gene will cause abnormalities in a cell, but that's usually not enough. A cell doesn't wake up one morning, get a mutation, and immediately turn into a malignant cell. It has to go through a multi-step process. Many genes have to be mutated, and we now know that there are, for every given cancer, multiple genes. This happens to be a one such cascade in colon cancer. So now you can ask the beginnings of the question which will animate, I hope, this discussion, which is, okay, so we now know that many genes are ultimately responsible for the eventual development of a malignancy. How are these genes different or similar across various malignancies and within a single malignancy. Everyone with me so far? Because that's actually a very, very important question. So again, to clarify the question, if you take 10 specimens of breast cancer, we know that there are many genes that will be involved in those 10 specimens of breast cancer. Are they the same? Are they different? How do they mix and match with each other? Okay? So I made a schematic here, again, just to reach a broader audience, but we'll talk about some of these in much greater detail. So here's the schematic. Here's a woman who has breast cancer, and you have the capacity, as we do, to put a dot, and you can imagine her whole entire genome is on this sheet of blank paper, crisscrossing like a snake. All the genes in her genome crisscrossing like a snake from gene 1 on chromosome 1 to the last gene, hypothetically, on the last chromosome on that last edge of the paper, not drawn to scale, obviously. And you have the capacity of putting a dot where every gene is mutated in her breast cancer. So this is her fingerprint, as it were, of her breast cancer. A second woman walks into the clinic, into your same clinic, maybe has exactly the same kind of tumor, at least in terms of pathological criteria, looks the same under the microscope, is 10 centimeters or 6 centimeters big, same right breast, same quadrant, etc. You perform the same genetic fingerprinting, and now you begin to see an interesting and important pattern. And that is that you'll see some genes that are common between these two cancers, but some genes that are different between these two cancers in terms of the mutations that these two cancers have. And here's a third example of one, and in this case, there's actually even more differences. So although there are some commonalities between these three individual specimens of breast cancer, we're only talking about breast cancer, there are also some striking and important differences. And you can begin to organize these in ways that are, that basically take the more common genes and make big peaks out of them, the less common genes and make small peaks out of them. We've done this work in leukemia. We've also done this work in lymphoma. This has been a worldwide effort to try to characterize and capture the level of genetic diversity within a single tumor subclass. And you get a map that looks like this with big peaks and small peaks. And in actuality, this is from Vogelstein's paper, from Bert's paper, but there are other examples of this. For colorectal cancer, 38 specimens here, and the peaks and troughs look like this. So you have very common mutations that are common across multiple cancers, multiple specimens of the same cancer, pardon me. You have, so those are the big peaks, the intermediate size peaks and small peaks for the unique ones. Now, it's important to remember that these big peaks are almost certainly, I'm saying almost, and I'll come back to that, almost certainly involved in the drive, as driving mutations in cancer. In other words, they're almost certainly involved in driving the behavior of the cancer cell. The small mutations are much more mysterious. They are obviously present much more rarely, present in one particular cancer, not other cancers, but they may also be responsible for the behaviors of that one particular cancer. It's very important to remember that idea. And one of the big tasks within the cancer world has been to figure out the role of each one individual mutation in driving the behavior of that cancer. So let's let that thought rest for a moment and focus on those big peaks. Those big peaks, as I said, if we could target those big peaks somehow using medicines, we would have personalized medicines for that cancer. That mutation targeted in one particular cancer should, if successful, be able to change the behavior of the cancer cell and hopefully have therapeutic effect. This is just basically the same information. This is from our own work in leukemia, showing the same information. I'm not going to dwell on that for a second. So, but going back to this idea of targeting I've used just the same schematic of colorectal cancer, although obviously the spectrum of mutations is different in different tumors. And this is an example that we began to see in the 1990s and 2000s of being able to target with exquisite specificity these driving mutations in particular cancers. And there's probably no better example of this than chronic myelogenous leukemia, CML, a disease that I treat. This is a picture of Brian Drucker, one of the physician scientists who really began this research program. It's a very wide research program, many other people involved. But Drucker and others showed that if you use this molecule called Gleevec, you could essentially inhibit the gene product made by this mutation. It happens to be a fusion product. And if you inhibited that, much like a lock to a key, a precise lock, precise key, you could turn off that key. This compound, by the way, is synthesized by human beings. Doesn't exist in nature. It's an astonishing thing. Human beings made that sort of key to that lock, and you get profound effects on the cancer. here is actually from the pivotal trial. It's a little dark, so I'll just point it out to you. From the pivotal trial of using the usage of imatinib or Gleevec in chronic myelogenous leukemia, survival curves looking at, on one hand, the inexorable death of patients. These are Kaplan-Meier survival curves over time on the x-axis, and the percentage of people alive on the y-axis. And you see that with standard chemotherapy, you would get terrible survival. Most of the people would be dead in about 5 years. But with Gleevec, it's really a flat line. So this totally transformative effect on this particular leukemia, and continues to be transformative today. This kind of idea was then repeated in the 2000s by a host of other drugs. This is an example of another one, this again using the same schematic. This is a drug that targets a HER2 gene amplification in breast cancer. A substantial fraction of breast cancer has the gene amplification HER2. This is the patient 0, or one of the patients 0. This is actually the first woman to enroll in the trial of Herceptin, the drug that targets that gene amplification. Her name is Barbara Bradfield. She had metastatic HER2-positive breast cancer, was treated. She was the first person on trial, and astonishingly still alive today. So this is her 18th year of profound remission from her metastatic HER2-positive breast cancer. One of the most striking cases, happened to be one of the first cases. And then this, of course, is the data from that pivotal trial for Herceptin in HER2-positive breast cancer, and shows very clearly on the right side patients treated versus patients not treated. Now remember, 2 points here. The point number 1 is that in order to even qualify for this trial, you had to have Herceptin, you had to have HER2-positive breast cancer. In other words, already the idea was that there was a match between the kind of breast cancer that you had, its molecular markers, its genetic markers, in this case, HER2, and the fact that you were responsive to therapy. If you used Herceptin on patients who don't have this marker and this gene amplification, of course, the medicine won't work. So this is really much like Gleevec, one of the earliest examples of the power of precision medicine at work, because you begin to see that if you appropriately match a good drug to a appropriately matched, genetically matched tumor, you get profound effects. That's the good news. The bad news is that, as you can see in the pivotal trial, if you had metastatic HER2-positive breast cancer, metastatic, so spread in multiple sites in your body, then although you get clearly a response to Herceptin, nonetheless, even then, after about 50 months or 60 months of treatment, even those patients relapse, and many of them will die as a consequence of their breast cancer. So there are 2 principles that come up here. Number 1 is that, at least in these early trials, targeting is essential, but targeting is not enough. So we have to somehow manage to move the compass beyond just single targets or genetic targets in that particular cancer. And I'm going to now talk about what happens sort of next as we move forward. The first thing that became clear is that if you now took patients who did not have metastatic breast cancer, so whose cancer had not spread, in other words, if you detected those early enough so that there was local tumor, removed it, and then gave Herceptin, all of a sudden you begin to see, in contrast to this, this sad but unfortunate, although as I said, successful trial with Herceptin, you began to see really important, impressive successes. So this is Herceptin after surgical removal. In contrast, so this is essentially, if you think about it conceptually, early detection or pre-metastatic detection, followed by the use of a targeted therapy. And now you begin to see powerful successes. So here you have on the right, this is again a trial from 2005. This has been repeated several times. Now you begin to see 90% or even 95% survival rates and 85% disease-free survival rates at 5 years and even 10 years after Herceptin treatment for HER2-positive breast cancer. So what have we done here? We have taken 2 paradigms, very important paradigms, early detection or appropriate detection, coupled that with a molecular targeted therapy, and that's been a success story. And I want you to remember that, because we will come back at the end of the talk to that paradigm over and over again. How do we get there? How do we get to the place in cancer that we can couple the appropriate detection of a tumor as early as possible and couple that with a molecular targeted therapy? Because it seems to me that that's where precision medicine for cancer in particular will be and should be going. So the question is, okay, those were great examples. So we had an example of Gleevec for CML, or imatinib for CML. Imatinib is the formulary name for Gleevec. Herceptin for HER2-positive breast cancer. And those were great examples because those were tumors where a target was clearly available. So you had HER2, you found a medicine for it. If you detected the tumor early enough, then it would be surprisingly successful. Similarly with Gleevec, if you could find the mutation BCR-ABL, you use Gleevec, particularly in the chronic phase of the disease. Again, very successful. But not every tumor, as we did more and more genetic sequencing, not every tumor turns out to have such a readily available target. So this is from our work in leukemia. This is a typical panel that we get. None of these have currently any targeted therapies available. So that's the second question that's being thrown up. What if you don't have a target that's available? What happens then? Well, we've started exploring answers to that question as well. And the answer to that question lies somewhat in going back again to this gene, the gene panel, as it were, to the mutational spectrum. So it turns out, obviously, that genes in cells don't live in isolation. They communicate with each other in pathways. And certain pathways are active. These pathways, for instance, will take signals from the surface of the cell down to the nucleus, or from the nucleus and affect the metabolism and growth of the cell. The genes themselves may not be mutated, but sometimes the pathways may be active in a cancer cell. I'll give you an analogy that'll help you think about this in a second. But one way to think about this is that not only are there obviously mutations that are specific to cancer, we talked about that already, but in fact, in every cancer cell, there are pathways that are activated. These pathways, for instance, are consuming resources. They're forcing the cell to grow despite the fact that there are signals, maybe signals in the environment to tell the cell to stop growing. And what if, even if you couldn't target the individual mutated genes, what if you could target the pathways? And again, one way to think about this, and it's helpful to think about this, is think about the cell as a complex machine. This complex machine, obviously in a cancer cell, in this complex machine has certain parts that are broken, and we talked about this already, mutations. But these mutations, these broken pieces, don't live in isolation. They communicate with each other, giving rise to complicated networks, or giving rise to complicated pathways, as case may be. And I've isolated one portion of the machine that may be responsible, for instance, for immune escape. Another portion of the machine that's responsible for growth. Some other portion that's responsible for metabolism, and so forth. So what if we could now, rather than targeting the mutations, as with imatinib or with Herceptin, if you could now basically cut off or switch off these more complex network problems? It's an analogy that engineers and certainly biologists should get very easily, because this happens all the time in any complex system. And this has been, these sort of pathways or arenas have been described as the hallmarks of cancer. This list is constantly expanding. I think there are about 8 or 10 in this particular list, but really have been described as various ways in which cancer cells really differ from the normal physiology of the cell. And the question is, could you now essentially target one or two pieces of this? So this led to a very, very powerful idea in the 2000s, which was, okay, let's now essentially characterize cancers along these hallmark pathways and try to now direct therapies against these hallmark pathways, not BCR-ABL and Gleevec for chronic myelogenous leukemia. Let's go beyond the sort of Herceptin for HER2-positive breast cancer or tamoxifen for ER-positive breast cancer. Let's think in a big way. Let's lump all cancers together, all comers, characterize them based on their pathways, their molecular pathways that are abnormal, and try to direct therapy against that. Very powerful idea, and I would say a 1.0 idea, the first attempt to do this. And this was the so-called Shiva trial. We really need to focus on this trial because it tells us what to do and what not to do in the future. So this trial was carried out in France, had 741 patients. And what they did is that they did molecular profiling of individual cancers. And by that I mean whether you had lung cancer, breast cancer, brain cancer, whatever kind of cancer you had, these cancers were profiled. And the doctor could decide, he or she could choose based on 3 pathways to give you an appropriate drug. Okay? Note the difference between the Herceptin trial and this kind of trial. In Herceptin, you're saying only breast cancer. You have to have that molecular target, HER2. You get Herceptin, hopefully with early detection, and you move on to the trial, right? Here, we're saying, let's forget about all of that. Let's take all cancers, molecularly profile them, put them into 3 lumps, 3 categories, and give the drugs based on that. Everyone with me so far? So what was the result of that trial? It was profoundly negative. So this was a surprising result. This was a 1.0 trial, but surprising result. But basically, if you use a molecular targeted agent versus treatment at physician's choice, number one, look at the rather dismal survival curves, and no difference. And in fact, if you subdivided it by the pathway, you don't need to know the names of the pathways. Similarly, really no signal, maybe a little marginal signal for the third one, but no signal. So what happened? This is the moral lesson. This is where we need to move from. So something must have happened. We lost information in moving from Herceptin, HER2 positive breast cancer, BCR-ABL positive leukemia, to the big lumping. So we have to now go backwards. And that's where these initiatives, that's why we're here today. We're here today to figure out what to do next. That led to a big editorial called Sitting Shiva on the Shiva trial, which asked the question, what went wrong? Why could we not use this kind of idea to lump all patients into the same sort of big bucket categories and ask the question, could you deliver appropriate therapy? Well, the answers could be patients could develop resistance, drugs could be not potent enough, and the path, maybe we don't know enough about the path. After all, these were only 3 pathways. There are hundreds in an individual cancer cell. So where do we go from here? Well, the answer is actually already coming out from what's happening. Number one is we have to go back somewhat to remembering what the cancer is. We're not there yet that we can sort of really lump together cancers based on these simple understandings of pathways. And I'll tell you why that works. So how does that work? So what do we do exactly? Well, one thing we've begun to think about as a community is one drug is not enough. So what if we add combinations of targeted therapies? Remember with Herceptin or with Gleevec, we're using single agents for single mutations. What if we put in 5 or 6 or 7? Number 2, what if we could use immune therapies? What if we add to that with immune therapies? Obviously, if we had more potent inhibitors. And in the last case, what if we had to just test every individual cancer empirically on a case-by-case basis for its susceptibility to one pathway or another? In fact, the answer is we're doing all 4 of these at the same time. I'll give you examples of all 4 of them as we finish up. Combination therapy. So does it work? Well, once again, if you remember the cancer, for particular kinds of cancer, if you identify particular targets and particular pathways, it does tend to work. How do we know that? We know that from multiple myeloma. So multiple myeloma is a great example. It's the one tumor where in the 10 years of my practice, the combinations of targeted therapies, I say targeted because, again, they're not specific to the mutations, but rather are targeting pathways in the multiple myeloma cell, has been transformative. How do we know it's transformative? If you had multiple myeloma, you walked into the clinic in 2001, before we had some of these therapies, we had only 1 or 2, your survival curve looks like that. If you were diagnosed between 2006 and 2010, your survival curve improves dramatically. Obviously, this is retrospective data, should be taken with a little grain of salt. If you walk into the clinic with the same stage multiple, these are matched for stage, by the way, with the same stage multiple myeloma in 2010 to 2016, that curve flattens out to about 0.8 percentage surviving progression-free at 5 odd years. Now, why is that happening? That's happened because in multiple myeloma, at least we can use 3, 4, maybe even 5 now targeted therapies in combination. Single agents don't work, combinations agents do. What's the moral of that story? We have to develop combination agents for cancers that are targeting individual separate pathways and don't have overlapping toxicities. Very, very clear for multiple myeloma. Okay, the second example is an example that's really been sort of raging through the literature, and that is, what if we added immune therapies to this? And there are a variety of immune therapies. I won't dwell on all their details, but the essential idea is, can we make the cancer cell now visible again to the immune system? And if so, will the immune system clear or eliminate the cancer? This is the trial that shows the success of that therapy. This is in smoking-related non-small cell lung cancer. Again, that's a tumor that I had not expected us to have an impact on during, at least in my lifetime. But a combination of targeted immunological therapies in that case has shown a remarkable effect. And then the possibility is to take individual cancers and test them for individual susceptibilities to drugs. We are doing that. Several other people are doing that, the empirical testing of individual cancers. We basically take an individual cancer, add the panoply of drugs that are available, and then try to return to those patients a drug that only works for them. So where do we end up? What's the moral of the story here? The moral of the story here is that through all of this, a kind of picture is emerging for cancer therapy. And the picture that's emerging is that, again, if we combine early detection, biological annotation, and personalized therapy, then we tend to have successes. When one of the areas or one of the nodes of this triangle goes missing, we don't tend to have successes in therapy. And the job of personalized medicine, and this is the challenge here, is not just to therefore think about personalized therapy. That's one end of the triangle. But to really try to fill all the three ends of the triangle as much as possible. Obviously, early detection, and I should say prevention. Because the more we silo personalized medicine, the history shows us that the chances are that we will have lack of successes. Whereas if we combine these sort of the triangle, that's actually going to be helpful. The question that all of this raises is, does this mean that we'll have to go back to an area or go forward to an area where every single cancer has to be treated sort of this way, found early, biologically annotated, and a unique combination of therapies will have to be found for that cancer? We don't know the answer to the question. We hope that in this second phase, as we move forward again to Shiva 2.0 or Shiva 3.0, I'm just using those, there'll be different names for the trials. As we move forward to these trials, that somehow or the other we will begin to lump again so that we can now recategorize the universe of cancers along new axes. And that will help a lot. Otherwise, you can imagine the challenges of delivering individualized therapies for individualized cancers along this triangle. So that's I think, the big moral of this story, that this requires a huge collaborative effort. I suspect that for instance, in the early detection is an arena where it's not just a biological problem. It might be a problem with imaging. It might be a problem with biomarker discovery. It might be a problem that people from the people who work on nanosystems biology can help, because it seems to be a problem of a different kind of scale. The biological annotation problem also seems to be a problem that involves computational work as much as deeply as just biological annotation. And of course, therapeutics involves physicians and physician scientists. Just to emphasize that that's the kind of collaboration that we need to move the clock forward in terms of the next step. I'm going to leave you with one last slide, which are the challenges slide. What happens? What are the concerns here? The concerns, of course, are how do we counter the costs? This is as we launch this gigantic mission for cancer therapy and for potentially other diseases. How on earth are we going to manage if we have to deliver this at a scale across the United States? How do we handle resistance? Is there a maintenance schedule? Once patients have responded to one particular personalized therapy, will they need other therapies down the road? Will those have to be personalized as well? And a big question here, which I've already talked about, if you find the tumor early enough, can you really dial that backwards until you get to the role of prevention? So again, a huge congratulations to the involvement in the effort, but I wanted to show you what the roadmap for cancer has looked like through its history, through its recent history, and highlight some of the challenges and provide what I think might be an appropriate sort of what I call a triangle, where you might be able to get we might be able to get the kind of astonishing responses that we hope to get in personalized therapy. Thank you very much.